Hi everyone, welcome back to chemistry. This will be the first video in our chapter 5 lecture series, which is all about chemical reactions. So we've talked about how different chemical compounds form, we've talked about ionic compounds versus covalent compounds, and now we want to talk about what happens when we react those compounds. So in order to understand chemical reactions, we first have to think about something called the law of conservation of matter. And this law states that the amount of matter in a system, sorry, let me get to yellow here. The amount of matter in a system is conserved. Or in other words, the amount of atoms that you start with needs to be the amount of atoms that you end with. So you'll notice over here, we've got the black circle in the middle is carbon, and then the white circles around are hydrogens. So we start off with 1 carbon and 4 hydrogens. And then we have, it looks like 4 oxygens, right? 1, 2, 3, and 4. So if in the end of our chemical reaction, we need to have the same type of atoms and the same amount. They can be bonded in different ways, but we didn't lose or gain any of those atoms during this chemical reaction. So another way of stating this is that in a chemical reaction, matter is neither created nor destroyed. And this is probably the most common way that you'll hear this law of conservation of matter kind of mentioned. Another way you could think about this is if you start with 100 grams of your substance, after the reaction, and that's what this arrow is, right? This is kind of before your reaction, and this is after, on the right side of the arrow. If you start with 100 grams, you need to end up with 100 grams, okay? You shouldn't have gained or lost any matter. They can be different things, right? This is mercuric oxide changing into mercury and oxygen after the reaction. But we still have 100 grams. So if you add up these two masses here, you should still end up with a total of 100 grams, and you do. Okay, so why does this matter? So chemical equations are these things that we use to represent the process of a chemical reaction. So this up here is a chemical equation, right? And I said to the left of the arrow, right, on the left side is your before picture, right? And then that's before the reaction. And then on the right side is your after stuff. So things that you get after you carry out the reaction. So before and after. So chemical equations are written just like that, where you have, something that you're starting with, and then you've got your arrow here, and then something that you're ending with. So you start with HGO here, and you end up with Hg and O2. Now, for these chemical equations, it takes a lot of work to write out the names of these chemical compounds. So that's why we spent so much time learning how to write these, chemical formulas, right? That's a formula for mercuric oxide. This is a formula for mercury. This is the formula for oxygen, and so on. So you don't have to write so many letters. And you'll notice I have these arrows kind of written here. So let's take a look at this first arrow. This first arrow here points to this S. And then you'll notice some other arrows pointing to the other things that are in parentheses. What do you think the S, the L, and the G stand for here? Yeah, so these are actually the state that matter is in. So at the start of our reaction, we have mercuric oxide in the solid state. As a solid, that's what that S stands for. Then after we carry out the reaction, we have mercury as a liquid in the liquid state and oxygen as a gas in the gaseous state. Okay, so those subscripts, we call them, those show you what state your compound or element is in. Or sometimes you'll just hear me say chemical species. You can also have something called aqueous. You can be in the aqueous state. So sometimes you'll see AQ in parentheses, and we always put these in parentheses like this, okay? And that's just to show, hey, now I'm naming a state and not an atom. But you'll also sometimes see AQ, and that stands for aqueous. So let's make a note of that. Oh, I'm so bad at spelling this. I think it's spelled like that, aqueous. And that just means dissolved in water. Dissolved in water, aqueous. All right, so those are what those subscripts mean. Then you'll see some other parts of this equation. So we've got our arrow here, which signifies kind of like the before slash after picture. And then we've got this, what color should I do? Let's do green. Then we've got this plus sign here. And that shows that we have made two different things. So we've made, you know, our mercury in the liquid state and our oxygen in the gaseous state. So this kind of just means and. We always represent that with a plus sign if we've made two separate species. All right, and then let me erase some of this, and I want to just make one more note before we move on. And that is that so far, I've just been calling everything that's on the left side of the arrow before and everything on the right side of the arrow after. But chemists actually use special terms for this. So anything on the left side of our chemical equation, right, that's what this whole thing is a chemical equation. Anything on the left side of our chemical equation is called a reactant. So this is the reactants side. And anything on the right side of the arrow is called our products. Products, the things that you're producing. So on the left side, we've got the things that we're reacting together, so reactants. And on the right side, we've got the things that we're producing, our products. What products are we making? Okay, and then they're just separated by our arrow. So instead of saying before your equation or before your reaction, I'm going to start saying reactants. And instead of saying after your reaction, I'm going to start saying products. So what are the products of this reaction is a question I could ask. And then you can say, oh, Hg in the liquid state and O2 in the gaseous state. Those are both of our products that we make. So just some new vocabulary there. All right, so we said that according to the law of conservation of matter, whatever atoms we start with, we also need to end with. They can be bonded in different ways, right? But they need to all be there. So if I start with 2 atoms of hydrogen and I add 2 atoms of oxygen, I need to get out 2 atoms of hydrogen and 2 atoms of oxygen. But right now, do you notice a problem? Yeah, I don't have 2 atoms of oxygen over there. The way that this equation, this chemical equation is written right now, I don't actually have the right number of atoms of each element on my product side. So I don't have the same number of atoms of each element in my reactants as my products. So I'm violating the law of conservation of matter. And that's illegal. Not so much a law. It's not illegal in the sense that, you know, you're going to get in trouble, but it's, you know, it's violating one of these laws of nature that we notice, that we've observed time and time again. So this just doesn't happen. So we need to make sure that we do something called balance this chemical equation, which means that the number of atoms on the right need to equal the number of atoms on the left. So the way that I like to do this is I personally like to draw a line right under my arrow here, separating my reactants from my products, the things I start with from what I end with. And then I list what types of atoms I have. So I have hydrogen atoms on the left, and I have oxygen atoms on the left. Okay, just listing what types of atoms I have, not the number yet. And then on the right side, on the product side, I should have, right, the same types of atoms because of that law of conservation of matter. And I do. I have H's and I have O's. Okay, I have hydrogens and oxygens. And now it's our job to make sure that we have the same number of each type of atom on each side. All right, and then you'll notice these little dashes here that I've got in front of each of my chemical species. And those dashes are actually so that I can leave room for something called the coefficients. So coefficients. And those are going to go here, here, and here. Coefficients. And what those coefficients do is they allow us to change the number of those types of chemical species, to change the amount of those chemical species that we have in order to balance the chemical equation. Why do we have that? Why can't we just change some of these numbers here? Why can't we just change those numbers? What happens if I put a different number here? For instance, over here on, sorry, let me make that a little more clear. Over here on H2O. What if I put a 2 there? What happens? is this H2O if I put an H2, if I put a 2 there? Is that still H2O? No, that's H2O2. That's hydrogen peroxide. That's a very different thing than water, right? We drink water every day. I really don't recommend drinking hydrogen peroxide. So you can't change those subscripts, because remember, we just did a whole chapter talking about how important it is that we need to name these compounds with prefixes to let us know exactly how many of each atom we have. And that's what these are letting us know, right? The number of those atoms in those compounds. So we're not allowed to change those. We can't change those subscripts. But what we can do is we can say, well, I made more of my water, or I put in more oxygen, or I put in more H2s, okay? So I know this sounds a little weird at first, so just let's try this out. So the way I like to do this is I like to put a 1 in for my coefficients, just to start with. And what that's going to do is that's going to assume that I have one, or at least one, of all of these different chemical species. And I'm going to change these numbers. That's allowed. You can change those coefficients in front, but you can't change these subscripts. So I start with 1, and then what I do is I list, if I have, assuming I have at least one of each, right? Then I'm going to count how many atoms I have of that type. So looking over here on the left at H2, I've got in that H2 molecule, right, hydrogen bonded to itself, I've got 2 hydrogen atoms, right? That's what this 2 here is telling me. So when I write my number here, what number am I going to write? Yeah, 2, because I've got one H2 molecule that has 2 hydrogens in it, okay? One H2 molecule that has 2 hydrogens in it. What if, and I'm not going to do this yet, but what if I did change this coefficient to 2 in front of hydrogen, H2? How would that change the number I've written here? Well, now I've got 2 H2 molecules. So as a side note, right, H2 looks like this, right? We've drawn the Lewis structure for H2. So it's 2 hydrogens bonded together. And now if I've got a 2 in front, that's saying, well, I have 2 of those H2 molecules. So now how many total H's do I have? Yeah, 4. So this would now be a 4 here. Okay, so that coefficient gets multiplied by the subscript here. So 2 times 2 is 4, and that's how I got that 4 there. Or you could think of it as, I have added another H2 molecule. I started with just the top one, and then I added this next one. And now I've got, that changes the total number of hydrogens I have. Okay, so that's how coefficients work, but we'll keep practicing. So let me get rid of all this. And we'll just go back to 1, just because I said let's start off with 1 of each. So if I have a 1 there, this 1 gets multiplied by this 2, right, to show I have 2 hydrogen atoms. All right, so for oxygen, now let's see for oxygen. I've got a 1 in front, which means I have 1 of this O2 molecules, right? So I've got 1 O2 molecule with how many oxygens total? Yeah, 2, right? Because this 1 in our coefficient gets multiplied by the 2 there. Okay, so that's going to be a 2 here. All right, now on the right side, I've got 1 in front of my H2O now. So that 1 is going to get multiplied not only by this 2, but also by the imaginary 1 on that oxygen, right? If you don't see a number there, that just means you have 1 of those atoms. So we can count with that 1 for our coefficient. How many hydrogens do we have? Hydrogen atoms. Yeah, 2, right? Because this 1 gets multiplied by that 2. And then how many oxygens? Yeah, 1, just 1, right? Because this 1 gets multiplied by the imaginary 1 that's there. 1 times 1 is just 1. So you'll notice I'm always multiplying these coefficients by the subscript, by the number of each of those individual atoms that we have. Okay, so is this equation balanced? Do I have the same number of atoms on the left as on the right for each type of atom? No, right? My hydrogens are good. So looking here, I've got 2 hydrogens on the left that I put into my reaction, and I got back out those 2 hydrogens. So hydrogen's good. But oxygen, right? I put in 2 and I got out 1. That's not right? That violates the law of conservation of matter. So we need to fix that. So what are we going to do? Are we allowed to change this number here? Can we put a 2 there and fix all of our problems? No, illegal. We're not allowed to do that, okay? So what can we do? What can we change? Yeah, the coefficient, right? I can change this 1 in front to something else. And when I'm doing that, I'm just saying, oh, actually, instead of getting out 1 molecule of H2O, I'm getting out some other number of H2O molecules, right? Okay, so let's go ahead and change that. What do you think we should change that coefficient to? It's not 1. It's not 0 because we know we make at least one of them, right? We're saying that this chemical reaction is taking place, right? So how many, what can we do? Yeah, let's change it to 2, right? Let's just try the next high up number, right? So we'll change it to 2. And when we change that to 2, how does that change these numbers over here? Well, now we've got to multiply that 2 by our coefficients. So 2 times 2 for hydrogen is 4. And 2 times imaginary 1, right, is 2 for oxygen. Okay, well now my oxygens are balanced, right? But my hydrogens are off now. So what should I do? Now I can go back to the other side, right? And I can't change this. That's like set in stone. I'm not changing the type of chemical reactant I put in. I'm not changing that, but I can change the amount I put in. So the amount is going to change, right, to 2. And when I do that, this 2 for hydrogen, now I'm saying I've got 2 H2 molecules, which means 2 times 2 is 4. Okay. I'm not going to touch this coefficient because these are balanced, right? I don't want to mess with that anymore. So now what this is saying, big picture, is that this is the ratio that these reactants react in to produce our products. Or in other words, I'm putting in 2 H2 molecules and 1 O2 molecule, and getting out 2 H2O molecules. Okay, that's the lowest ratio that these can react in without violating the law of conservation of mass. So this is what we see when we do this chemical reaction with H2 and O2. This is the ratio it reacts in. So kind of interesting. All right, and then this slide just has some tips for balancing equations, and some of these aren't going to make a ton of sense yet until we start practicing, but I'll read through them. So the first tip is that you want to determine the correct chemical formulas, right? So something like, for example, H2O. That's a formula, right? For each reactant and product. So you want to make sure that you wrote the chemical formulas correctly. And then you want to write what's called a skeleton equation. So just like up here, before we put any of these, before we balanced it, it was just, these parts were empty, okay? So that's what a skeleton equation would be. Then you're going to count the number of atoms of each element that you have in the reactant and the product, okay? So just like I said, right, how many, assuming you start off with at least 1 of each thing, how many do you start with on the left and how many do you end with on the right? Okay, and then you got to start changing your coefficients in front of your formulas, but keeping in mind you never want to change the subscripts. Then you want to check each of your atoms to make sure that they're equal on both sides of the equation, right, like we did up here. And then you want to make sure that all coefficients are in the lowest possible ratio. And if you need to, you can reduce. So for instance, What do I mean by that? Lowest possible ratio. So for instance, what if you were working on this and you automatically decided to change this number to 4? Okay, so what if you had a 4 up here, 4 for H2O, and then you had a 2 for O2 and a 4 for H2? This is not necessarily incorrect in terms of how you balanced it, right? It is balanced, right? A 2 to 1 to 2 ratio is the same as a 4 to 2 to 4 ratio. But it's not in the lowest ratio it can be in. Okay, so if you see that all of the numbers are divisible by some number, in this case, they are all divisible by 2, you want to go ahead and divide by 2 for each of those, and that's going to give you your lowest ratio. Okay, a little bit mathy, so if you need any help with, math review on that, just let me know, and I can help you kind of reduce those reduce those numbers. All right, so let's try this out together. So we've got, my first step is always, I like to draw this line, separating my reactants on the left from my products on the right. And then the next thing I like to do is I like to list the types of atoms that I have on both sides. So I have carbon atoms, right? I have hydrogen atoms, and I have oxygen atoms. And for me personally, if I write it CHO on the left, I'm going to put it in the same order on the right. Okay, and just double checking, right? I've got C's, I've got O's, and I've got H's, CHO, CHO. Yeah, this looks good. These are the types of atoms that I have. All right, so then I want to assume I have one of each for starters, and we're going to change those coefficients, but for right now, I'm going to assume I have one of each of those things. Okay, so if I have one C2H4 that I'm putting in, let's go ahead and count how many atoms I start with. And let's go for carbon first. So for carbon, how many carbon atoms do I start with? Yeah, 2, right? Because this coefficient gets multiplied by that 2. So I have 2 carbons that I start with. I also start with, 4 H's, right? 4 H's. And these dashes, these are just dashes. I'm not subtracting anything. I just like to put them there to show, how many carbons? Oh, 2. How many hydrogens? 4. All right, and then how many oxygens? Yeah, 2. All right, on the right side, I've got, let's see, we got to count these. So for carbon, looks like I just have 1, right? 1 carbon. So 1 carbon. For hydrogen, looks like I've got 2, right? That 1 gets multiplied by the subscript 2. So I've got 2 hydrogens. And then for oxygen, it gets a little tricky. So the rule here is that if you see the same type of atom in 2 different chemical species, right? I've got oxygens in my CO2 molecule and in my water molecules here. Then you need to count the oxygens in both of those compounds. So on the left for CO2, just looking at that first chemical species, I've got 2 oxygens, right? Because my coefficient's just 1. So 2 are coming from my CO2, 2 oxygens. 2 oxygens. And then from over here, I have how many? Yeah, just 1, right? That 1 gets multiplied by an imaginary 1 for our oxygens. We have 1 oxygen here. So I have a total, and so many students, I see this, want to multiply these numbers. We actually have to add them, okay? So think of this adding sign here. You have to add those oxygens up together. So I've got 2 from my CO2 and 1 from my H2O. So I need to add that. That's going to be a total of 3, right? And you could think of this also with a picture, right? So if I've got, CO, this is just my CO2 molecule, and then I've got, H, and you'll learn why I'm drawing it like that in the future. And then I've got my, water molecule. Looking here, right, I've got my 1 oxygen here and 2 here. That's the 2 over here that we see. And then I've also got another one here, right? So 3 total oxygens. Okay, I just wanted to explain that because students get confused with that quite a bit. All right, so 3 oxygens on the right, and let's see, 2 oxygens on the left. So I'm noticing these oxygens are not balanced. The hydrogens are also not balanced. Whoa, and the carbons are also not balanced. So none of these atoms are balanced. And what do I mean by that? I mean, the number that I start with is not the same number that I end with of each of those atoms. So that is violating the law of conservation of matter, and we need to fix that. All right, so for carbon, we have 2 on the left and 1 on the right. So what can we do? Yeah, what if we just make, I don't know, let's change this coefficient over here to, let's go 2. Okay, just to fix that carbon. And when we do that, we need to kind of make sure that we're reflecting that change down below. So for carbon, when I change that, now I have 2 carbons. And how does that change our oxygens? Well, now I've got 4 oxygens coming from this molecule and still only 1 over here. So that's 5 oxygens. So we got to fix that. I didn't mess with my hydrogen, so I don't need to change that. So carbon's happy, but oxygen's not happy. So what can we do? Well, I'm noticing that I've got 2 hydrogens on the right. So what if I change this coefficient on the right in front of H2O to 2? Well, how is that going to change things? So now I've got 4 H's over on the right, which is great because I've got 4 on the left, right? But I threw off my O's again. So I have 4 O's coming from my CO2. And how many coming from my H2O? Yeah, 2. So I've got 4 O's here and 2 O's here. So when I got to add those together, right? So I've got 6 total O's over here now because 4 plus 2 is 6. Okay, so what can I do? Well, I'd like to not have to mess up my carbons and hydrogens now because they're balanced now, right? So is there something I can change here just on my oxygens to make that equal 6? Yeah, that's going to be a 3, right? So that's allowed. We can make that a 3. We can change how many O2s we put in. And when we do that, right, 3 times 2 is 6, which is the same as on my right. And that's going to give, me 6 oxygens. All right, one more example and then we'll end this video. So what if we have polyatomic ions? That gets a little bit crazy. The best tip that I have for polyatomic ions is if you see that they haven't broken up on the left and on the right, then you're going to treat them as a unit. So what do I mean by that? Well, we've got lead Pb bonded to 2 NO3s over here. So looking at NO3, what's NO3 by the way? Yeah, nitrate. So I've got one compound with a nitrate on the left, and I'm seeing that I still have my nitrate intact over on the right, right? I didn't split it up into N's by themselves and O's by themselves. We've still got our polyatomic ion kind of bonded together. It's just now it's bonded to Na instead of lead. But that's okay. So as long as you see them that it's not broken up on the right, or after the chemical reaction, you can treat it as one unit. And I'll show you what I mean by that. So I'm going to, like always, draw my little line between my, reactants and my products. And then I'm going to list what species I have. So I have some lead atoms. And now I have some nitrates. And I'm just going to put a parentheses around there. And then I've got my NAs. And I've got some Cls, right? And then on the right, I've still got PBs. I've got Cls. I've got NAs. And I've got NO3, 1 minuses. So, like I said, right, our NO3 minus sticks together, so we're going to treat it as one unit. So I'm not going to break that up into, nitrogens and oxygens. You can, and it'll still work when you balance these. It just takes a lot more effort, and it can get really confusing, and several times I've done it, and I've just convinced myself that it can't be balanced because it's so challenging. So my biggest tip is to treat them as one unit if you can. And that just means if they haven't broken up. All right, so And now, just like any other one of these balancing equations, we're just going to follow my steps. So we're going to put 1 in front of all of our coefficients right now, assuming I have 1 of each of everything at least. And then we're going to count how many we have now that we've got that 1 there. All right, so let's go ahead and do that. So we've got 1 lead, right? And then how many nitrates? Remember, we're treating this as 1 unit. Okay, so how many nitrates do we have? And I'll keep these highlighted, actually. I think that's helpful. So notice, right, we've got our 2 here. So that means how many nitrates? Yeah, 2 nitrates, right? 2 nitrates. Because this 2 is telling me I have 2 of everything in the parentheses. All right, so then how many sodiums? Yeah, just 1. And how many Cls? Yeah, just 1. All right, and on the right, how many leads, Pb? Just 1. How many nitrates? Yeah, just 1. Again, it's just 1 of them, right? There's no number outside of it there. Na, we've got 1. And chlorine, how many chlorines? Yeah, 2. 2 chlorines. Okay, so I'm going to get rid of those parentheses. All right, so it's not balanced right now, right? We've got our leads are balanced, right? We've got 1 to 1. Our sodiums are balanced, but our nitrates and our Cls are not balanced. So we got to fix this. So what can we do first? Well, I think I'm going to change this coefficient in front of my sodium nitrate to 2. And that's going to give me 2 of these nitrates and 2 sodiums. But that's okay. I can fix the sodium on the left as well. All right, so I've changed that. And what you'll also notice is that I don't personally like to erase the number that I have, that I started with. I like to cross it off and put a new number down once I change the coefficient in front. And that's just so that I can, if I make a mistake, I can go back and just erase this step, right? And go back to my previous coefficient, because sometimes you'll realize, no, putting that coefficient there doesn't really help, and I actually want to change the coefficient somewhere else, okay? But for now, yeah, I'll just show you there. And now let's see. So now we've thrown off our sodiums, our NAs, so let's go ahead and change the coefficient here to 2 and see if that works. And a lot of this is trial and error, so let's see. So we got, now we've got 2 NAs when I change that coefficient, and 2 Cls. All right, and actually that looks like it's balanced, right? I've got 1 Pb on the left and 1 on the right. I've got 2 nitrates on the left and 2 nitrates on the right. I've got 2 NAs on the left and 2 NAs on the right, and 2 Cls on the left and 2 Cls on the right. So this is balanced. So when we carry out this reaction, right, what does this mean? We're going to put in 1 PbNO3 compound plus 2 NaCls, and we're going to get out 2 NaNO3s and 1 PbCl2. That's the ratio, the lowest ratio that these are going to react in, that's still going to obey the law of conservation of matter.